Now we're moving on to the next section of DevCon, where we are going to hear from the Julia folks. So we have actually maybe small but really vibrant community of people using Julia with Odyssey. And first we have a talk by Kyrylo, which I'm going to pull up. It's pre-recorded.
Hello, my name is Kyrylo. I'm working at Tufts Clinical and Translational Science Institute, and translation is exactly what I'm going to talk about today. Translation of cohort definitions to SQL queries using a library called FunSQL. FunSQL is a library for constructing SQL queries. It is released under open source MIT license. FunSQL is written in Julia, but this talk is not going to be specific to Julia or any other programming language. I just want to mention that FunSQL can be invoked from R using Julia call package. Why did we create FunSQL? FunSQL is designed for translating complex specifications, such as AMOP cohort definitions, into analytical SQL queries. FunSQL allows us to approach such queries systematically. With FunSQL, when we discover a frequent query fragment, we can extract it and convert it to a reusable component. With enough such usable components, assembling even the most complex SQL queries against the most unwieldy database schemas becomes easy and fun. I will start with discussing why translating cohort definitions to SQL is so difficult. I will also talk about different types of SQL query builders and where FunSQL is placed among them. The rest of the talk will be dedicated to examples, where I will demonstrate how to build queries for a MOP common data model and how to extract fragments of such queries and make them reusable. Translating rule-based cohort definitions into SQL can be challenging. This diagram represents one such definition, adapted from the Book of Odyssey, an occurrence of acute myocardial infarction during an inpatient visit. This is a relatively simple cohort definition, but translating even such a simple definition can still be difficult and error-prone. But what is it exactly in these cohort definitions that makes assembling the corresponding SQL challenging? I can identify three reasons. First, the logic of the cohort does not have a fixed, uniform shape, but instead expressed as an arbitrary series of steps, where the number and the type of steps can vary between different definitions. Second, implementing each step may require advanced SQL features, aggregate and window functions, complex join conditions, correlated subqueries, common table expressions, and so on. Finally, rather than translating just one definition, you may want to write a program that translates any given cohort definition into SQL. While it is already hard to write SQL for just one cohort definition, dynamically generating SQL for an arbitrary definition is orders of magnitude more difficult. Before we dive into translating cohort definitions, let me describe the place of FunSQL among other query building libraries. These libraries can be divided into two classes: those that build SQL by assembling the SQL syntax tree, and those that build SQL by assembling a data processing pipeline. It is important to clearly distinguish between these two classes because while the interfaces of these libraries can look deceptively similar, their methods of operation are fundamentally different. This difference is demonstrated by these two queries, one written in Laravel Query Builder and the other in FunSQL. If we ignore the surface syntax, both queries are exactly the same and can be visualized as this pipeline of 5 processing components. Now the question, what output do you expect this pipeline to produce? It may come as a surprise, but these two libraries generate different SQL queries, which produce different outputs. Laravel Query Builder constructs SQL by incrementally assembling a SQL syntax tree. Each component of the pipeline processes a partially assembled SQL query. For example, the where component augments a SQL query by attaching the where clause. In a select statement, the position of the where clause is fixed, so Laravel knows exactly where to insert it. Notice that how components are ordered in the pipeline is not significant. You could put where component before or after order and limit, and the results in SQL will stay the same. The FunSQL query is represented by exactly the same component pipeline. But FunSQL interprets this pipeline as if it actually transforms data. The filter component in this interpretation takes input data and filters it by the predicate condition. Of course, FunSQL does not process the data directly. FunSQL also generates a SQL query, but this SQL query must process data according to the data transformation logic of this pipeline. Generating such SQL query is harder because the pipeline does not have to comply with the rigid clause order imposed by the SQL grammar. In FunSQL, pipeline components are divorced from SQL syntax, so we need some other way to justify whether some component is acceptable or not. Here are some principles that any pipeline component in FunSQL must satisfy. First, all pipeline components, in fact all expressions in FunSQL, must have well-defined data processing interpretation. Any pipeline component can be interpreted as if it transforms data, so that for any input we can tell the corresponding output. Of course, this interpretation is completely virtual, but it is essential for keeping query pipelines coherent. Second, any pair of components can be composed as long as the output of the first component is compatible with the expected input of the second component. This is different from SQL, where restrictions are expressed not in terms of data, but in terms of syntax. For example, group by cannot be followed by a join, or a window function cannot be used in a where clause. FunSQL has no such restrictions. Any expression can be used anywhere in a query, for as long as the shape of the data allows it. This is exactly the property that lets us fearlessly create and use new pipeline components. At the same time, we do not want to sacrifice any SQL capabilities. FunSQL should support aggregate and window functions, correlated subqueries, lateral joins, recursive queries. All of these features should be available for us to use. Finding an appropriate data processing interpretation for existing SQL features was a major challenge in designing FunSQL. Finally, it's time for the fun part of the talk, examples. The goal of these examples is to demonstrate how to build query pipelines and how to extract reusable query components. I start with a simple query that finds a concept by vocabulary in concept code. The FunSQL code for the query is on the left. On the right is a pipeline diagram that represents the query. I find that pipeline diagrams are easier to comprehend than pure code, so I will use them extensively for demonstration. But you always assemble FunSQL queries by writing code. This query works as it is, but we can go further. Let's take this pipeline and convert it to a reusable component. This component is similar to from in that it takes no input. It outputs one row, a SNOMED concept with the given code. This is a good start. We build a brand new component by composing standard components, from and filter. To demonstrate more complex examples, we need more standard components, such as join. If we have two datasets and we need to align them vertically, we use a join. Joins in FunSQL work exactly like in SQL, with one important distinction. Let me demonstrate this issue on an example where we want to take a concept and produce its immediate children. In a mob command data model, concepts are related to each other through concept relationship table. To find child concepts, we build a pipeline with two joins, one join connecting the parent concept to concept relationship, and the other join connecting concept relationship to the child concept. However, there is a complication. Both the parent and the child concepts use the same column names, so we need some way to disambiguate them. This may seem like a trivial matter, but it is very important for composability. How different query frameworks deal with naming conflicts? SQL offers table aliases, but aliases require name bindings and naming scope, which are lexical properties and not compatible with data processing interpretation. Another query framework, dplyr, simply renames columns that are in conflict. FunSQL uses neither table aliases, nor does it mangle column names. Instead, FunSQL allows us to nest columns using the as component. To refer to a nested column, we must use dotted notation, parent.conceptID. We can use the as component to disambiguate between the parent and the child concept and finish the query pipeline. But we could do more than that. We could extract a part of this pipeline and make it to a new component, which we simply call children. This component has one input and one output. It takes a concept set as an input and outputs a set of their immediate children. In general, when we join two tables in FunSQL, we keep main table bare and use as to nest the other table. We can go further and pre-join a table with all the other tables that are related to it. If we mark these joins as optional, they're eliminated from the generated SQL query unless the columns from the join branch are actually being used. You must ensure that optional join does not change the cardinality of the output. This pipeline produces a fragment of a database schema with a focus on a particular table. Of course, we could convert this pipeline to a reusable component that we call a hierarchical view. Let us get back to exploring operations on concepts. Suppose we want to combine the parent concept and its immediate children. For this purpose, we can use append component, which FunSQL translates to a union all SQL query. Append lets us horizontally combine two or more data sets of a similar shape. Now suppose we want to see a concept itself together with not just its immediate children, but all of its descendants. Now I know that MOPCDM provides a derived table concept ancestor specifically for this purpose. But in this example, I don't want to use a derived table. I want to rely only on the concept and concept relationship. Then how can I approach it? To get all descendant concepts, we need to combine immediate children, children of the immediate children, then children of those, and so on indefinitely. You may recognize the process of feedback here, and FunSQL supports it with the iterate component. Iterate is translated by FunSQL to recursive SQL query. Again, we could isolate a fragment of this pipeline and convert it to a new reusable component. This component, called withDescendants, takes a concept set as an input and outputs the same concepts together with all of their descendants. Another useful operation on concept sets is exclusion. In this example, we define an acute condition as a descendant of a general condition, excluding descendants of an old condition. Of course, we can make exclude its own pipeline component. This component takes two inputs with one output, just like a join. Proceeding this way, we can build our own little language for constructing concept sets. We are no longer using SQL notions and verbs. We migrated to the language and vocabulary of our own subject domain. At the same time, the queries that we assemble are still in SQL and still compatible with regular SQL operations. In the same query, we can bring different languages from different subject domains and combine them with the standard SQL verbs. In the example here, we are building a component to retrieve conditional occurrences by concepts. And this component will accept concept sets constructed using our new concept set language without any additional effort on our part. For the last set of examples, I'd like to demonstrate how we can build algorithm-oriented components with aggregate and window functions. But first I must show how these functions are specified in FunSQL. FunSQL notation deviates from SQL syntax in order to make it composable and to give it data processing interpretation. In order to use an aggregate or a window function, a FunSQL pipeline must contain respectively the group or the partition component. These components add extra data to each output row, just enough data to make it possible to calculate the value of any downstream aggregate or window function. Both types of functions use exactly the same notation, and the type of the function is decided by the fact whether it is applied to the output of group or the output of partition. I will demonstrate how this notation works in the following examples. The first example uses a window function to pick, for each patient, their latest visit. Of course, we could immediately extract a reusable component that for each patient picks the first row ordered by some key. The next example uses an aggregate function in order to find top 10 most popular care sites and their visit counts. Again, we could easily extract a reusable component that for any given column calculates top n most common values and their counts. This component can be very useful for data exploration. To make this component even more useful, we could add the count for the remainder of the data. We adapt the previous example using a window function to separate top n values from the remainder and an aggregate sum to evaluate the final counts. Such pipelines of aggregate and window functions applied in a sequence are often used to solve algorithmic problems. This example shows a pipeline that merges overlapping intervals in 3 easy steps. First step identifies intervals that begin a new era. Second, assigns the era number to each interval. And the final step groups the intervals by their era numbers. What's important, of course, is that once we crafted this pipeline, we can convert it to a reusable component and apply it to any input of our choice. For instance, we can apply it to cohort episodes, to collapse episodes within a window, or apply it to test data, to test the component itself. For my last example, I'd like to demonstrate how group component can be combined with join. Remember how we constructed a hierarchical view of a table by joining all its related tables with optional joins. Because this join must not change the cardinality of the output, it may appear that you could only add joins in one direction, many to one. But it is possible to join in the other direction, one to many, as long as you group the target table. You could use such joins to immediately evaluate aggregate functions. It's time to wrap up my talk. Getting back to the problem that I stated at the very beginning of the talk, I hope I convinced you that you could solve this problem by building a collection, or better say a language, of reusable components that allow you to assemble queries using the verbs and the notions of your specific area of knowledge. This language is embedded in FunSQL itself and thus immediately compatible with the core FunSQL or any other language embedded in it. The concept of an embedded domain-specific language is well known in general programming, but not in database querying, most likely because of poor means of abstractions offered by mainstream query languages. With FunSQL, we could change this and make it a practical and functional tool available to the working data analyst. Thank you for your time.
Okay, that was great. So next we have Jacob Zelko, someone who I've met through Odyssey and have had a lot of great conversations with, and really excited to collaborate with. And Jacob works in Julia. He's going to kind of talk about applying some of these tools, FunSQL, to doing network studies in Julia. So take it away, Jacob.
Awesome. Hello, everyone. Thank you so much for coming to my talk, Julia for Global Health Research and Collaboration. I'm so honored to be presenting here today at the 2023 Odyssey DevCon. My name is Jacob Zelko. As some of you may know of me through the Odyssey forums and also the open source community as my moniker, the Cedar Prince. I'm involved with the open source development community, such as working on Julia packages like javis.jl for animations and visualizations, the Julia Health community, and through my my blog, The Cedar Ledge. Furthermore, I'm the chair of the Julia Community Development Fund, and I'm a mentor for the Julia Gender Inclusive Outreach Program in the Julia community. I'm currently right now a researcher at Georgia Tech Research Institute and the Centers for Disease Control. However, I'm excited to announce that I'm actually going to be becoming a applied mathematics master's student at Northeastern University with the Rowe Institute starting this fall. So I'll be transitioning hats here very shortly. And just for some fun, here's some artwork of the Cedar Prince, things that the Julia community can build with Javis, and also just me on some random adventures across the globe. So just to level set and recap on what the goals of Odyssey are for intents and purposes of this talk is based on the book of Odyssey. There's 3 main goals, which is, it's an international open science collaborative dedicated to observational health research, establish open community data standards, and finally, make end-to-end solutions of translating observational data to reliable evidence. In this talk, I'm really going to focus on points 1 and point 3. Now, what I found really great in a lot of variety of different projects is to drive projects with a problem. And so what I want to talk about first is, what am I doing in OHDSI? As many people in the OHDSI community might be aware of, I'm currently a principal investigator for an observational health network study focused on developing a package to characterize populations with chronic mental health conditions, investigate prevalence of mental health care and utilization of mental health resources in rural and urban communities, both in the United States and across the globe. Some of the specific targets is to identify vulnerable populations and their characteristics, examine loss to follow-up, and conduct large-scale observational health research through the wonderful collaborator network that we have here in OHDSI. And so where is the project today? So currently, as it stands, the project has been deployed with collaborators across the globe. I'm happy to say we're in the final weeks of the ongoing study at a lot of these different collaborative sites. And the stretch goal that, still have my fingers crossed for, we'll see if we can make it, is to have a total patient population cohort of around 100 million patients. And one of the things that this project has been great for driving forward is not only driving forward, research in mental health and even health disparity research, but also driving new efforts in novel research tooling. And that brings me to kind of the purpose of this talk today, which is, what is Julia? So Julia is a programming language that I've been using to write a variety of different observational health research tools that examines data from the OMOP common data model. In fact, usually the tagline that goes along with the Julia programming language is that it walks like Python, meaning it looks a little bit like Python syntax, if you're familiar with that. It feels like it a little bit. It talks like Lisp, meaning it's very strong, very powerful, and very flexible with everything that you want to do. And finally, it runs like Fortran, which means that's very speedy. So a brief history of what the Julia programming language actually is it was created at MIT in 2012. It was specifically, at the time, designed for scientific, numerical, and high-performance computing, but has since moved on to kind of fill a niche, also similar to some of the other high-level languages in general-purpose programming. And it's also very powerful in addressing what is known as, quote, quote, the two-language problem. Now, if you've never heard of the two-language problem, you might have also heard of it as, I think, Oosterhoff's problem or Oosterhoff's paradox, which is, in a sense, you start out prototyping maybe a data pipeline, analysis pipeline, software, what have you, in a high-level language or one language, such as, Python, R, so on and so forth, to get the idea out the door and show that, this project or this software can really work. However, then what ends up happening is that you have a project and you either have massive amounts of computation that needs to be done, massive amounts of data need to be processed, and due to the performance needs of these problems that you're running into, oftentimes as a developer or a software developer or engineer, you need to switch to a more performant language, such as things like C, C++, even Rust or Java. Now, I mentioned that Julia is supposed to be fast and that addresses the two-language problem. So let's talk a little bit about how it actually does that. Now, before we get started, I do want to give credit to Robin Dietz for this example from his intro to Julia talk at Detroit Tech Watch. Just want to let you know this following example is a little contrived, but it gets at the idea of what I mean by solving the two-language problem. Most often in the wild, you'll run into much more complicated two-language problem scenarios, but this should, as a sense or as a general idea, give you a sense of what I mean by Julia solving the two-language problem. So take, for example, here. This is a function that is a naive implementation of the sum function. For those who are not aware of what the sum function does, it generally comes with a variety of different languages. Python, R, all have it to some extent, where the sum function will take a list of items, be it list of integers or float values or what have you, and sums them all up together into a final result. So seen here, we have a function called mySum, which I'll go ahead and execute. So as you can see, we just defined mySum, which is naively implemented within the Julia programming language. Next, let's go ahead and generate some fake data to test this particular function with. So what we'll do is we'll go ahead and run the ran function and say we want 1,000 elements of type float 64. So right now we just generate a list of 1,000 data elements of float 64. And additionally, we do some additional processing because in Julia, the rand function returns decimal values. So what I'm going to say is I want to broadcast or multiply element-wise each element within my data variable by 10. So I'm saying for every single value in data, multiply it by 10. That's what this period star operator signifies here. And then if you're familiar with R, we also have the piping syntax. So what I'm going to say next is I'm going to throw this list that's just been multiplied by 10, and I want to say round every single value in this resulting list that was just multiplied by 10 and round it to an integer. Again, we're using this idea of broadcasting to round everything to an integer of around 1 or 2 values. And finally, we can go ahead and time my sum using the Julia benchmarking package benchmark tools. So as you can see, it's already pretty fast, 68.878 nanoseconds. So that's pretty speedy. But I think we can get it faster. So in this case, this is where the Julia solving the two-language problem starts to come into play, which is this idea of you don't necessarily need to leave Julia to actually have the performance improvements that you might see if you switch to another more performant language. So in this case, I take the original mySum function and I do some annotation of the code. So if you notice, the two biggest differences in this code now is I've applied something called a macro to our code. There's actually 2 macros that I'm using, which is inbounds, which is telling the compiler for Julia, hey, don't bother checking for making sure we're going to go out of bounds for going through this loop of elements. I assure you it is okay. So the compiler's like, okay, phew, I don't need to check for errors. And then SIMD, which says to the compiler, hey, also when you iterate through this loop, you can go out of order. It's okay. Just make sure it all gets back into result. And the compiler's like, okay, that sounds great. So like we can go ahead and get that set up. Now let's go ahead and time it. So 46.89 nanoseconds. So that is still pretty fast, but let's see how it compares between the two different functions. So we'll go ahead and run the loose benchmarks again for mySum as well as myPassSum. So we have for mySum 70 nanoseconds. So let's just go ahead and put that into here. And we have about 46 nanoseconds for the second version. So in this case, we actually have a nearly 152% increase over the original mySum function. Now, again, as I mentioned, this is a rather somewhat contrived example just to show the idea of what I mean by Julia addressing and solving the two-language problem. In a nutshell, what you can see here is that if you need the higher performance of, say, managing or understanding, millions or billions of data elements, you don't necessarily need to leave Julia to get that performance. In fact, you can actually optimize within the language itself. So not only are you able to stay within Julia and keep doing your workflow within Julia, you can bridge to that performance and get the performance that you need within the ecosystem as is. And speaking of bridging, both inspired by the general notion of this OHDSI DevCon, as well as the Julia community itself, Julia is actually great for building bridges. So for Julia plays really nicely with other programming languages in existence. You're able to actually directly interoperate bidirectionally with languages such as R, Python, MATLAB, Java, other ones not listed here. And you're able to keep using all the same familiar tools that you want to use within Julia without necessarily having to give up on the performance. So for example, I could call R from Julia, or R could call Julia, depending on the workflow that you need. And I've actually done it multiple times. And to that end, just to drive the point home, I had a really exciting conversation with Hadley Wickham at one point talking about, this idea of using Julia with R or instead of C++. And, Hadley Wickham and I were chatting, and Hadley was just saying like how at the time when he was writing some of the tidyverse, Julia didn't really exist yet or wasn't really performant enough yet. And he said now as Julia is quite mature, he said it might be a great idea to actually partner up R with Julia as a backend instead of something like C++, just to make the barrier to entry maybe even a little less for getting the performance that we need in the R ecosystem, for example. Now, enough kind of talking about the generalities of Julia. Let's get into actually talking about how we can use Julia for different sorts of observational health research. So one of the big things within the study that I've been piloting is patient characterization. And additionally, we've developed tooling within Julia to actually do some characterization. So for this, the goal was to create characterization of patients across 3 axes who have at least one prior diagnosis of strep throat. This is just a demonstration example that I'm going to walk through with this slide deck. And additionally, for this somewhat small characterization study that we're going to run right now, we're going to use the concept set of streptococcal sore throat, which is coded this nomad ontology. We're just going to have one concept ID within our concept set. So to go ahead and get started with this main characterization that we're going to run is that all we need to do is activate the project. For all Julia projects, you only need a project.toml and a manifest.toml. These specify package dependencies and their versions all the way down to transient dependencies, such that by just running using package activate, package instantiate, you'll be all set to go as long as you have Julia installed on your computer. So I just went ahead and ran that cell. And in this demo, we'll be using data frames, which is Julia's data frame handler for easily manipulating data, very similar to Tibble and dplyr. OMOP CDM cohort creator, which is a tool that we've developed in Julia Health to iteratively create patient cohorts from databases utilizing the OMOP CDM. Health sample data, another one that we created, which provides sample health data for a variety of different health formats and use cases. And finally, SQLite, a Julia interface to the SQLite library. Now we'll go ahead and use, in this example, data provided from Eunomia that is stored in SQLite format. In compliance with the Apache 2 license, we're actually able to bundle up some of the data from Eunomia within health sample data. And seen here, we go ahead and download it onto our machine using Julia. And as you can see, this package tests to make sure that Eunomia is downloaded into my computer, which I already did prior to this presentation. And to connect to the database, we'll do the following with SQLite. So we'll go ahead and run this, and the connection has now been established. Great. So in an analogous way to database connector or SQL render, we have to generate connection details for this particular pipeline. And if to do that, we do the following. So we're going to import the OMOP CDM cohort creator as OCC. If you're familiar with Python, this should be very similar or almost exactly the same as aliasing that you might see in Python land. So we'll go ahead and run this code. And as you can see, what Julia does is sets the database dialect to SQLite, the global schema to nothing, because with SQLite it doesn't have a schema. And then it'll also generate Julia representations of each and every single one of the OMOP CDM tables found in this particular example. Note that in the future, my hope is that OCC will not have you required to type in this, database details, generate tables thing. This can be extracted away from the user in the future. But for now, it's still here. Now let's go ahead and start running our characterization. So let's find all patients with strep throat. So to do this, we'll just go ahead and run the cell. And the number of patients with strep throat is 1,677 people. And if you're curious to see what this variable looks like, actually just a one-dimensional data frame with person IDs and their counts. And again, just to let you all know, this is fake data just generated from Eunomia, in particular, Cynthia. So no worries there. Now, we found all the people with strep throat, so let's go ahead and find their race. All right, there we go, very simple enough. We take a very functional approach with OCC in that each of these different functions, such as get patient gender, get patient race, all will return an additional column attached to the original person ID. Moving forward, we'll go ahead and use the most complicated function, which is get patient age group. Now, get patient age group, what that will allow you to do is automatically bucket all the different patients within the OMOP CDM cohort or base cohort and say what age groups that we want. So in this case, we go up from increments of 5 from 0 all the way up to 109. People in the Eunomia data set get quite old. It's kind of funny. But with that being said, we go ahead and include these age groupings. And as you can see here, we developed an additional column called age group. And you can see here that we've appropriately mapped that person to the age group of 70 to 74. Now, as an aside, as you saw in the excellent presentation previously by Kyrylo about FunSQL, what I wanted to mention is actually every single one of these functions that I've been calling so far that directly call against the OMOP CDM database itself can actually be generated into SQL expressions because OCC is directly built on top of these wonderful nodes provided by FunSQL. It's built on top of FunSQL. So for example, we can go ahead and remove the connection object here and generate the original SQL that is actually being used to query the OMOP CDM database. And this is in SQLite syntax. Now, the reason why I wanted to call this particularly out is the fact that I've been able to use this successfully in a variety of different ways, such as chaining together and composing different SQL blocks or SQL queries together intelligently, auditing purposes, as well as to build a foundation for future sort of queries where perhaps maybe a SQL flavor is not supported just yet. I can use this as a foundation to generate the original SQL that I need, and then tweak it from there and deploy it into production into other projects. But this is great for auditing. I just wanted to take a second to both recognize FunSQL, as well as this capability built into OMOP CDM cohort creator. Now we can use dataframes.jl to go ahead and characterize each person by gender, race, and age group. This is just a simple join that you might do like within dplyr. So as you can see, we have one row with the person ID, the race concept ID, gender concept, and age group. And now finally, we can go ahead and group up our patients into population groups based on race, gender, and age group. What we're going to do now is going to go ahead and drop person ID because we don't want the person ID being shared. And we're going to go ahead and combine all these patients who fall into similar buckets together into one single data frame. Seen here, we now have a data frame that is 113 rows by 4 columns. And as you can see, there is a count column that says how many people are represented in this stratification breakdown. And finally, we're going to go ahead and execute a safety audit, which is built into OCC. For right now, we're just going to follow high-tech compliance standards, which removes small cells from a data frame. And as you can see, we went from nearly 120 rows down to 42 rows. And that's because we removed all cells smaller than 11. But yeah, so this is just a quick demo to show how you can do some basic characterization of patients within Julia using the OMOP CDM cohort creator tool and the tool chain available within Julia. And this provides your foundation for now going forward to maybe creating things like prevalence rates or other sort of analyses very quickly and iteratively. Now, starting to wrap up, so I just want to hit on some ways to get involved potentially within the Julia Health ecosystem. So right now, feel free to experiment with the Julia Health packages and ecosystem. We're investigating different projects around patient level prediction, course treatment pathways, and perhaps even ETLs built in Julia for OMOPification of data. And also drop into the future Julia Health meetings or even the Julia community through Slack or Discourse. And finally, I'll also be running a Birds of a Feather event at JuliaCon this summer, which is in Boston. So if you're in the Boston area, please let me know. I'd love to have you come by, listen to other Julians using how they think we can use Julia Health or just the tools within Julia to support and better global health informatics. And additionally, let's do network studies. So it's entirely possible, in my opinion, to conduct network studies in Julia. There's a growing network of sites that are friendly to Julia projects seen here listed below. And they'll enable more people and bridging to happen between both the Julia communities, high performance computing and computational science communities, and bring those people into the fold of the greater observational health research and health informatics communities. And just to conclude with some final thoughts from Dr. Alan Edelman, seen on the right, Turing Award winner for his pioneering work in distributed computing, which he used as actually the foundation for creating the Julia programming language. He's one of the co-creators. He said in a great talk called "A Programming Language to Heal the Planet Together," a programming language that can let humans talk to humans, create a community, create social action, and a system where everybody can work together. And he's talking about Julia here. But if I can further, if I can be permitted to extrapolate a little bit, on this quote. My dream is that, Julia can be, again, a language that can enable humans to talk together, create bridging between communities, and empower and drive equitable solutions in healthcare across the globe in such a way that is beneficial to all patients of all nationalities involved within any observational health research studies that we do globally in the future. And with that said, for sure, keep in touch. Here's my email, website, Twitch, on Odyssey team, Microsoft Teams. So please, don't hesitate to reach out. I'm happy to support in whichever way I possibly can. And just as a fun thing, before I drop off this talk completely, so Julia is really flexible. And in fact, this entire talk is actually just a Jupyter notebook. It's actually code itself. And if you're curious about actually running this entire demonstration for yourselves locally on your own computer, here's the code that was used to create this Jupyter notebook and this repository I'll share a link to in just a moment. So if you want to actually experiment with what I just showed and how these characterizations can work, please do so. And finally, here's Julia Help. And also here's the documentation for OMAP CDM cohort creator. We have a lot of tutorials that will walk you through how to get started, how to bridge between R and Julia, and how to just get started with this package entirely. So thank you all so much for your time. And I appreciate being able to present here today at DevCon. Thank you.